In this video, we're concerned with computing distances in XYZ space in R3 in 3 space. So how do we compute distances in this space? So we're going to start off with just a problem and talk through how we're going to compute the distance between these 2 points. Then we'll generalize this and come up with a formula given any 2 points in 3 space, figure out the distance between them, a formula for generating that. And keep in mind, distance in 2 dimensions, in 2D, so between 2 points, let's say x1, y1, and x2, y2, so between those 2 points, the distance between them will be, remember by the Pythagorean theorem, we talked about this in section 13.1, square root of the distances, or the differences between coordinates squared and their sum. So that gives the distance between 2 points in just 2 space. We're familiar with that. We've seen that a lot. So what about in XYZ space? Well, I'm going to first plot these points, 4, 4, 1, and 1, negative 2, 0. So let's see. So here's my x-axis. X, y, Z. We're going to go 4, 4, 1. 1, 2, 3, 4. 1, 2, 3, 4. And I'm going to need to go, let's put 1 up here. So that's 1. This is 4. This is 4. Should give us everything we need. So first I'm going to plot 4, 4, 1. So I'll do the part of this that's XY plane. So that would be about here. So that's the point 4, 4, 0. And then I'm going to take that up to a height of 1. About right here. So this is my point P. And now Q. All right, 1 in the x direction, negative 2 in the y. 1, 2. So here I am in the xy plane. This would be the point 1, negative 2, 0. Oh, and we don't have a height on this one, so that's just my point. Whew, that was nice. Negative 2, 0 there. And then, so now I can form a line in 3 dimensions between these 2 points. So notice it comes at us a bit and also up a bit. So this line, we want the length of that line. That's our distance between these 2 points. Again, it goes up a bit and kind of towards us a bit. All right, so I've also plotted these in a program that I like to use for this sort of visualization called Geogebra. So I've plotted these in Geogebra. Our point A here is the same as our point P from the last one. Notice that's 4, so this is our x, y, and z coordinates. So that's 4, 4, 1 is P, and then 1, negative 2, 0, that's our point Q. And again, here's that line between them. So how do we compute the length of this line between them? In 2 dimensions, we use the Pythagorean theorem. In 3 dimensions, we're going to use the Pythagorean theorem twice. Because if you notice this line between P and Q, it's the hypotenuse of a right triangle. Let me try and highlight it. This right triangle. That's one leg, that's another leg. And then the hypotenuse is the line that we're interested in. So there's one triangle. So if I knew the length of each of those legs, so one of these legs I do know. This has a length of 1 because we went 1 up in the z direction. So that length is 1. This length, though, is the hypotenuse of a different right triangle. Let me highlight that one. So B or Q all the way over here to C. And then this one. And both of those lengths, and then we have this being the hypotenuse of that triangle. And we know both of the legs of that right triangle. because negative 2 to 4, so this has a length of 6. And then from 1 in the x direction all the way to 4 in the x direction, so this has a length of 3. Okay, so that means we can use those two lengths, those are legs of a right triangle, to get the hypotenuse here. That becomes the leg of another right triangle, and we can use the Pythagorean theorem again to get the distance between P and Q. All right, well, let's calculate that. So first off, the length of this line segment, will be square root of 3 squared plus 6 squared. So that's 36 plus 9, that's 45. So this is square root of 45 is this length. Now that becomes, again, the leg of a different right triangle, now with a height of 1. So now square root of 45 by 1, and we want the hypotenuse there. So let's calculate that. So this is going to be square root of 45 squared, that was one leg, plus 1 squared, or square root of 46. So notice something cool that's happening here. When I do this second Pythagorean theorem, I get square root of 45, and then I square it. I get rid of the square root. So if we expanded the square root of 5, remember square root of 45, remember where this came from. That was square root of 3 squared plus 6 squared. So I'm going to expand that out. When I square it, this is going to look like square root of 3 squared plus 6 squared, but I'm going to square it, so this is really 3 squared plus 6 squared. There's my square root of 45 squared, plus 1 squared. So this is really, when we think about it a little bit harder like this, when we think of it just a little bit differently, we can see what the general formula is going to look like here. So this 3 represents the change in the x direction, this 3. This 6 represents the change in the y direction. And the z represents the change, or this 1 squared represents the change in the z direction. So what we're seeing here as a general formula, we should look something like this. Change in x squared plus change in y squared plus change in z squared, square root of all that. It's the three-dimensional version of the Pythagorean theorem. And that's pretty cool. So let's talk a little bit more about where that general formula comes from. I want to work it out in a little bit more detail. So yeah, how to find the distance between 2 points, x1, y1, z1, x2, y2, z2. Remember for a second what that looked like in 2 dimensions. So change in x, you can think about it with deltas if you want. Change in x squared, change in y squared. These are these quantities here. So 3 dimensions. Here's another little figure to help us visualize this a bit. So just what's going on here. See my 2 right triangles again. This one's the hypotenuse of another one. So we want this length here. That's going to be the difference in my x's. So that's going to be, looks like, oh. Right, okay, good. So that's my x1 and x2, change in my x. So this length is x2 minus x1. Let's see, this length here is my change in my y values, so that's y2 minus y1. And then here, this length is z2 minus z1. So we use these 2 legs to get this length here. That comes the Pythagorean theorem. So this length then is, let me draw it out like this. This length is square root of x2 minus x1 squared. And the order of the x2 and the x1 doesn't really matter, right? Because I'm squaring it, so it'll kill the sign on it. It doesn't really matter. You don't have to keep that straight. Just think of it as differences between the 2. So that's that length. And then I use Pythagorean theorem again. Let me put this maybe over here. So now this length, let me do it in green. In general then, we bring the z's into this. Will be square root of this quantity squared. Get rid of the square root. So that's x2 minus x1 squared plus y2 minus y1 squared plus, and then the this length squared. So that's z2 minus z1 squared. Square root of that. That's the distance between P and Q. x1, y1, z1, and x2, y2, z2. Difference in each of the coordinates squared, take their sum, take the square root. Hopefully you can see how that generalizes from the two-dimensional. It generalizes very nicely, and a lot of the things we're going to look at will generalize very nicely like that. And there's the formula once again, maybe a little bit clearer because it's, typed out instead of me writing it out. Okay, that's it for this video. I will see you next time. We'll talk about spheres and balls.